So, welcome to lecture series. So, we are discussing about the vector space. We have defined what is vector space. We have taken couple of examples of it. Before taking more examples and to give some sort of geometrical representation wherever it is possible, let me define one more terminology called subspace. Let V be a vector space. Vector space over a field capital F. If I say V be a vector space, then certainly there are two binary operations is also there, that is one vector addition and scalar multiplication. Then a non-empty subset W of a vector space is said to be subspace of V provided W satisfies all criterion or axioms of vector space with respect to vector addition and scalar multiplication. So, what I am saying that a non-empty subset W of a vector space V over a field capital F is said to be a subspace of V provided that W itself satisfied all the criteria of the vector space V. I mean W itself is again a vector space. So, let me consider that V equal to our F2, the space of all two tuples over capital F, and vector addition and scalar multiplication are defined like what we did last time with vector addition and scalar multiplication as for U and V belongs to V, U plus V equal to U1 plus V1 comma U2 plus V2. This is the vector addition, and C belongs to the field capital F. C star is equal to, I am defined as C U1 and C U2, where U is equal to U1 and U2, V equal to V1 and V2 please. So, this is my scalar multiplications. We know with respect to these two binary operation V is a vector space. So, if I just consider geometrically, see my V equal to F2 as if F is equal to a real number, then this I can say as a simply xy plane type of things. Okay. So, it is basically some sort of a xy plane type of, when it is all points in the xy plane please, that is my capital V please. Now, if I consider all the points on the x axis, let W equal to set of all the points like x comma 0. X belongs to your capital F. I mean all the two tuples where the second entry is 0. This means that this is all the points of the X space. So, we can immediately check it satisfied all the axioms of the definition of the vector space please. Therefore, W will be also a subspace of the vector space V please. Of course, it is very tedious to check all these 10 axioms for this set W suppose. Now, question is it possible to give a simple formula? One can use that formula to check the whether a given subset of a vector space is a subspace of the vector space or not. So, let me quickly give that formula first, so that after that if I take a different example, it will be easy to understand whether a given subset of a vector space is a subspace or not. Here for a subset of a vector space to be a subspace of it. So, what is the criteria for this one please? If I consider that W is a subset of a vector space V, then certainly with respect to scalar multiplications that W will satisfy it. Apart from closure property, all other property will holds good, alright, axioms of the word vector space only. So, if I can somehow show that a subset is closed and is an abelian group closed with respect to both vector addition as well as scalar multiplications, and with respect to vector addition in the abelian group, then we can say that that subset is a subspace of the corresponding given vector space. So, I can consider one standard results like this in terms of theorems. It is like this. A non-empty subset of a vector space V over F is a subspace of V if and only if for any U and V belongs to W and C belongs to F. C star U plus V belongs to your W. If this criteria is satisfied, then immediately I can say that the subset W of the given vector space will be a subspace of the vector space V please. Or since I am talking about if and only if, so if W is a subspace, then also this criteria that C star U plus V also belongs to W please. Now, let me give the if the criteria that C star U plus V belongs to W is satisfied, we want to say, want to show W is a vector space, as W is the subspace of V, please. I mean to say, I have to check with this given criteria that W satisfied closure property with respect to multiplications and W is a abelian group, because rest of the axioms with respect to scalar multiplication is a basically axioms of the B, and W is a part of it, it will satisfy it. So, therefore, I have to basically check all this set of properties, please. It is given to me for any C belongs to capital F and U and V belong to W, C star U plus V belongs to W. Given W is non-empty, so let V belongs to W, and we know -1 belongs to capital F. So, according to this criteria, according to star, I can say your -1 time V plus V will be also W. So, -1, this is star, please, this one. So, this implies that see -1 star V equal to minus V. So, this is equal to minus V plus V, which is equal to 0 belongs to W. Here 0 is 0 element of V. So, the 0 element of V also 0 element of W, please. I mean it is also inside W, please. So, this implies for any C belongs to capital F and U belongs to capital V, C star U plus 0 which is equal to C star U belongs to W, implies W is closed with respect to scalar multiplication. For any U and V belongs to W, one can write down C equal to 1 and 1 star U plus V also belongs to W. This implies U plus V belongs to W. This implies W is closed with respect to vector addition. So, W is closed with respect to scalar multiplication as well as vector addition. Now, I want to show, see, associate property will holds good by default, because this associate property is the inherent property of the vector space V. So, I do not have to prove whether W satisfied associate property or not. So, that property holds good by default. Associative property holds good in W also, since W is a subset of V. Now, I have to check existence of additive inverse. For additive inverse, we have for U belongs to W, -1 times U plus 0 also belongs to W. For U belongs to W, -1 times this is star, U plus 0 also belongs to W. So, this implies -1 Okay, star u belongs to W, that is minus u belongs to W. So, this implies additive inverse exists. Inverse also exists. Since W is a subset of V which satisfied commutative property, so commutative property will also hold good for W. So, W is an abelian group with respect to vector addition and is closed with respect to scalar multiplication. Thus, W is a subspace. So, W is a subspace of V. Now, other way is given W is a subspace of V. So, it is closed with respect to vector addition and scalar multiplication. Therefore, for any u and v belongs to W and C belongs to capital F, C star u, which again will be inside W, plus V will be also belongs to W. So, this criteria holds good in this case. So, we see that a non-empty subset of a vector space will be a subspace provided for any u and v belongs to W and C belongs to corresponding field, C star u plus V belongs to W. For sake of brevity or simplicity, I will not write down star, I will simply write Cu. So, if I write Cu plus V means there is a binary operation star, I mean scalar multiplication in between C and U, please. Okay. So, now onwards I will use this is basically Cu plus V belongs to W, please. Okay. So, this is with due permission from you, I am writing this one, please. So, let me take different example, please. Now, let V be a vector space over F. Over F means F is a field of scalar, and vector space means there is a definitely two binary operations are there, vector addition and scalar multiplications, and satisfied all the criteria of the definition, please. Let W equal to collection of only 0 element, that is collection of 0 element of V. Claim W is a subspace of V. How to prove it? I have to check whether the criteria for any U and V belongs to W and C belongs to capital F C star u plus v belongs to W or not. Since W contains only singleton element 0, 0 element basically of the vector space V. So, any scalar C, C star 0 plus 0 equal to C star 0, which is equal to again 0 element. So, therefore, this W is a subspace of the vector space V place. So, this is called the trivial subspace. It is called as 0 subspace. Similarly, if I take W equal to V, then also it is a subset of V and it is also subspace. It is also subspace of V place. So, these are the basically trivial subspaces of the corresponding vector space V place. Now, let me take other example please. Let V equal to collection of all 3 tuples. So, this is equally say F3, that F may be real number or complex number. Now, consider let W is equal to collection of all the V belongs to capital V such that V is of the form of say 0 comma x comma y, where x belongs to your F and y belongs to also F place. Now, we can quickly check whether this W is a subspace or not. We have for any u and v belongs to W. So, u equal 0 comma say u 2 comma u 3 and v is like something like 0 comma say v 2 comma v 3. So, the binary operation over n tuple space, that is component adding component wise. So, if I do that one is my binary operation vector addition please here, then we have u plus v equal to it is 0 and u 2 plus v 2 comma u 3 plus v 3. So, it is again belongs to W. So, what I mean to say you, if I consider over the Euclidean space x, y, z, all the points in the Euclidean space is my given vector space say V equal to F3. Here if I consider F equal to real number. Now, if I consider the W, W is a set of all the points which are first entry 0. This means that it will be over the, so it is a all the points in the yz plane. So, you see that all the points in yz plane is a subspace of the vector space V. Exactly same way one can check all the points on the xz plane is also subspace of V, and all the points over the x axis is also subspace of F3, all the points over the y axis is also subspace of F3. So, we can have many subspaces for this place. Let V equal to Fn place, I mean set of space of all n tuples over F place. So, this is a vector space with respect to vector addition and multiplication what I have defined last times. I will say that is my standard addition over the Fn, and that is multiplication what I consider as a standard scalar multiplication for the space of all n tuple place. And let W be the solution of the system of equations Ax equal to 0, where A is M cross N matrix over F and capital X is basically N cross 1 column matrix. Now, this W, what I am saying is the solutions of this system Ax equal to 0 will be subset of certainly of the vector space V equal to Fn. My claim is that it is also subspace. Claim W is a subspace of V. For any x1 and x2 which are solution of Ax equal to 0, we have A x1 equal to 0 and A x2 equal to 0. For any C belongs to capital F, we have C star x1 plus x2. I have told you I will not use star, I will simply write basically C x1 plus x2. My claim is that this is also solution of the system Ax equal to 0. We have, I have to prove that A multiplying to the C x1 plus x2 is equal to A C x1 plus A x2. So, this is equal to again C I can take common. So, A x1 plus A x2 which is equal to C 0 plus 0 which is equal to 0. So, this implies your capital Y equal to C x1 plus x2 is also solution of Ax equal to 0. This implies that W is a subspace of vector space. This one please. Okay. Let me take say another examples. Let us represent set of all M cross N matrices over capital F by F M cross N notation please. Okay. Let V equal to F M cross N please. Define vector addition and scalar multiplication as below. For A and B belongs to V, your A plus B I am defining as okay, where say A equal to Aij, your 1 less than equal to I less than equal to M and 1 less than equal to J less than equal to N. So, I am defining A plus B equal to Aij plus Bij plus. So, this is my addition please, and scalar multiplication as for C belongs to capital F and A belongs to capital B, C star A is equal to I am defining C star say Aij equal to as C into Aij. So, C is multiplied to each entry of the matrix F. Of course, I will say that this is the standard scalar multiplication for this set of elements. Okay. Now, with respect to these two binary operations, one can easily show that V is a vector space. Yes. So, this is basically I am giving as a homework, please, because the proof is exactly same what we did for the Fn, please. Okay. So, now I have taken my vector space is F m cross n over the F, please, and the vector addition and multiplication like this thing, please. Consider V is equal to F n cross n. So, I have taken m equal to n. So, which is also a vector space. Then consider W as collection of all symmetric matrices. That is, W is collection of all the A belongs to V such that your Aij equal to Aj for 1 less than equal to I less than equal to A n and 1 less than equal to j less than equal to n, please. Okay. Claim W is a subspace of V. Again one can show it that C times capital A1 plus capital A2, where capital A1 and A2 belongs to W. I mean A1 is symmetric, A2 also symmetric, then C times A1 plus A2 is also a symmetric matrix. So, I can leave it as this is also homework, please. Okay. Let me use a concept called linear combination. A vector beta belongs to V, where V is a vector space, is a vector space over F, is said to be linear combination of vectors there exist some distinct vectors, say V1, V2 and scalars C1, C2, Cn belongs to F, such that beta is equal to C1 V1 plus C2 V2 plus Cn Vn. This is basically it is C1 star V1 plus C2 star V2 and Cn star Vn, where the star is the basically scalar multiplication. For sake of simplicity, I have removed this star. If I write simply C1 V1, that is also meaningful, and it is basically saying that C1 star V1 plus C2 star V2, please. Okay. So, this is the definition of when one can say a vector of a vector space is a linear combinations of some vectors. Okay. So, fine. So, let me introduce some more terminology. Subspace spanned by a subset of a vector space. What is the meaning of this ones? Let V be a vector space over field capital F. Let capital S is a subset of V. I am not saying that capital S is a subspace of V, I am simply saying that it is a subset of V, please. Let capital L denote the collection of all possible linear combination of vectors of capital S. So, if I say that it is a possible collection of all linear combination of vectors of S, means that is over the field S capital F, that is I can write L is a some sort of collections, okay, this is something like C1 V1 plus C2 V2 plus something like Cn Vn type, where V1 V2 and Vn say belongs to capital S and Ci belongs to capital F. So, this is the collection of all the linear combinations of the vectors of capital S, please. This collection is a subspace. This collection is a subspace of vector space V. How? Consider S is a non-empty space, non-empty subset of V, please. Now, if I consider S is a non-empty subset of V, so for any linear combinations I will say that since the vector space is closed with respect to vector addition and scalar multiplication, so each linear combination is also element of V, please. So, therefore, I can say L is non-empty, please. Let U and V belongs to capital L. So, U is equal to, I can say X I V I equal to say 1 to some number such that V I belongs to W. Okay. So, this n is fictitious number, please. It S may contain 1, 2, 3, infinite, whatever may be. So, I am saying that your U is basically linear combination of the some element of capital S. So, I can write U is equal to something like this thing, and okay, and V equal to also will have some sort of similar expression. So, I will write down Y I and say V I equal to 1 to some index this thing. Okay. Then U plus V equal to, so I can write down simply X I V I for sake of simplicity, I equal to 1 to n and plus sigma Y I V I equal to 1 to n. So, this is equal to, I can write in a compact form X I plus Y I times V I equal to 1 to n. So, this is again a linear combination of the vectors of the W. So, this belongs to L, please. And for any C belongs to F, C times U which is equal to again C into basically sigma say X I V I So, this is nothing sigma C xi vi, I equal to 1 to n. This is again a linear combination of the, where this is now new constant, new coefficient C xi. Okay. So, it is also linear combination of the vectors of W. So, this is also belongs to L. Thus, this implies L is a subspace of V place. So, all collection of all possible linear combinations of the vectors of a W is a subspace of the corresponding vector space. Now, an interesting question may arise, it is like this. Let V be a vector space over capital F, and W1, W2, let W1, W2 be any two subspaces of V. Then W1 intersection W2 is also a subspace of V place. How to prove it? Proof is very straightforward. For since W1 and W2 both of them are basically subspaces of the corresponding vector space V. Now, for any U and V belongs to W1 intersection W2 and C belongs to capital F, C star U plus V belongs to W1 and C star U plus V also belongs to W2. So, this implies C star U plus V belongs to W1 intersection W2. So, we see that intersection of two subspaces is again a subspace. In fact, if I take the intersection of the n subspaces, again it will be a subspace place. Now, what can you say if I say that union of two subspaces, will it be a subspace? Now, these questions I can answer through geometry. What about union of two subspaces of a vector space? See, let me take our very well known vector space, that is F3 or R3 I can say. So, V is equal to say F3, set up all the 3 tuples. So, this is basically the collection of all the points in Euclidean space. This is basically Euclidean space please. Okay. Now, if I consider, so let my V is equal to F3 I have taken here, and W1 is equal to collection of all the points, say U belongs to V such that U is equal to of the form of say x comma 0 comma 0, and W2 is equal to set of all the V belongs to capital B such that V is equal to 0 comma x comma 0, something like this thing. So, this means that W1 is my x axis. So, this is my x axis, this is a y axis, this is z axis please. So, we see that W1 is the x axis and W2 is my y axis. Now, if I consider, let W equal to W1 union W2, then will it be a subspace? Answer is no. How? Let U belongs to W1 and V belongs to W2. So, this implies that U is equal to of the form of something like x comma 0 and v equal to something like 0 comma y comma 0. So, u plus v will be equal to the form of x comma y comma 0. So, this is the point in the xy plane. So, this point belongs to somewhere here. So, this is the point, this point u. So, let me represent u by the point say p1 and this is a say point as a q1, okay. That is my v. Then this sum of two points is a point here which does not belongs to your u w1 union w2. So, therefore, union not necessary to be a subspace, but it will be subspace provided I can conclude like this, Let me just take examples and then show what will be the possible answer, please. Let v is equal to f3 and w1 is equal to collection of all the points comma x comma y comma 0 and w2 is equal to, let me consider all the points x comma 0 comma 0. Now, you see, if I take w1 union w2, so w1 is my basically here xy plane, whereas w2 is my x axis. So, union will be again in over the xy plane. So, it will be a subspace again. So, if I consider two subspaces w1 w2, their union will be subspace provided one of them will contain other. That is the basic criteria, please. Let me introduce another terminology called sum of subset of a vector space. Let V be a vector space over F. Let W1, W2, Wk be subset of V. Then the collection of all points such that your W is equal to something W1 plus W2 plus Wk, where Wi belongs to W capital I, is the collection of all the point W is called as sum of subsets of V. If the subsets are subspace, then it is called sum of subspaces, please. So, we have defined what is subspace, we have defined what is intersection of subspaces is also subspace. We have also seen that union of two subspaces will be subspace provided one is inside of other. We have also defined what is sum of subset and sum of subspaces. Okay. So, we will continue in the next class. That is all today. Thank you.